One-dimensional kinematics of a point is the study of the motion of a point along a one-dimensional path. The point is shown as a small red dot. A one-dimensional path is also called a linear path because it can be drawn as a line. The linear path can be a straight line or a planar curve. Note that a circle is also a planar curve. Therefore, a circle could be a linear path, from a one-dimensional kinematics point of view. A spatial curve can also be a linear path. Note that the size of the point is infinitesimally small, relative to the length of the path, such that we can assume that the point has zero size. Note too that the width of the path is also equal to zero, such that the point is restricted to move only along the length of the path. Let's use the capital letter P to denote this point. Now let's define a second point on the path. We call this point the reference point, or the origin point. The point is usually denoted as point O, for origin. We call the signed distance between point O and point P along the path the position, or the coordinate of the point on the path. We will usually denote this position using the small letter x. We call it a signed distance, because the length can be either positive or negative. In this case, when point P is on the left of O, we are defining the length as negative. And when point P is on the right of O, we are defining the length as positive. One-dimensional kinematics can be defined as the study of x as a function of time, or x of t, where x is the position of a point on a linear path. Point P can represent an object of interest to us. This object can be, for example, a ball, a car, an airplane, a missile, a person, and so on, that is moving on a known path. For example, for a car, the path can be a highway. For a train, the path can be the railway tracks. For an airplane, the path can be the flight route between two cities. Point P is a point on the object of interest, such that the position of the point can be used to represent the position of the object on the path. So if a point that represents an object is moving along a linear path, then defining the value of x at any point in time completely describes the position of the object. In the previous slide, we looked at some linear paths along which a point P is moving. Since the position of point P changes with time, we can make a plot of the position of point P versus time. The vertical axis of the graph represents the position of point P, which we refer to as x. And time is on the horizontal axis. Note how point P moves according to this graph. At time 0, for instance, point P is on top of point O, which means that x is 0, i.e., the distance between point O and point P is 0. At time 2.5, x of t is equal to 3. And you can see that point P is a distance of 3 units from the origin O. At time 5, point P has moved back to point O. And you can see from the graph that x of t is equal to 0. And at time 7.5, x of t is equal to -3. And point P is a distance of -3 units from the origin O. Note that on the curves, x represents a signed distance along the curve. In other words, x is the length of the red line. It is not the straight line distance between points O and P. The purpose of one-dimensional kinematics is to calculate using simple calculus, the position, velocity, or acceleration of a point P, that represents an object of interest to us, given only partial information about the point as a function of time. This slide shows the relationship between the various kinematic variables. A straight arrow indicates that one kinematic variable can be calculated directly from the other one. A squiggly arrow means that you can calculate a kinematic variable from another variable, but you need a little more information. For example, from x of t, which is the instantaneous position of the point as a function of time, we can directly calculate the average position, the average velocity, and the instantaneous velocity. Alternatively, if we know the instantaneous velocity, we can then directly calculate the average velocity, the average acceleration, and the instantaneous acceleration. As the squiggly arrow indicates, we can also calculate the instantaneous position. If we know some more information, namely the value of the position at a point in time. From the instantaneous acceleration, we can directly calculate the average acceleration. We can also directly calculate the instantaneous velocity. If we have some more information, namely the value of the velocity at a point in time. Next, the transformation relations implied by the straight and squiggly arrows will be derived. Note that if you say position, or velocity, or acceleration, generally it means the instantaneous value. Now let's derive the relation between the instantaneous position of a point as a function of time, and the average position of the point in a time interval. Note that if you say position, without specifying instantaneous position, or average position, then it generally means instantaneous position. One useful kinematic variable that is sometimes needed in practice is the average position of a point in a certain time interval, i.e. between two instances of time, say t1 and t2. Suppose we only know the value of the position of the point at time t1, or x of t1, and at time t2, or x of t2. We can propose a formula for the average position, x bar t1 to t2, of the point, to be equal to x of t1 plus x of t2 divided by 2. For example, suppose Alice is walking from home to work. And all we know is that at 8:10 am, Alice is 1 kilometer away from home. And at 8:30 am, Alice is 4 kilometers away from home. Then using the formula above, we can estimate that her average position within this time interval is 4 plus 1 over 2, or 2.5 kilometers, which is halfway between t1 and t2. We can easily demonstrate that this estimate of the average position may be completely wrong. For example, suppose Alice didn't walk at a steady pace from t1 to t2. Suppose she stayed around her starting point of 1 kilometer for most of the time interval, and then suddenly just before 8:30, ran quickly to her ending point of 4 kilometers. In that case, the average position of Alice in the time interval is closer to the value of 1 kilometer than the value of 2.5 that the formula gives. Also, it is possible for the average position between time t1 and time t2 to be smaller, or larger than x of t1 or x of t2. For example, suppose Alice is at 1 kilometer at time t1. Then after that moves to the left of x of t1. And stays there until just before t2. Then runs quickly to x of t2. In this case, the average position of Alice in the time interval could be less than x of t1. In the last slide, we suggested a formula for calculating the average position, using only 2 points, namely the starting point and the ending point. And we talked about how this formula is inaccurate. A more accurate approach is to find the value of the position of the point, at other random instances in time between t1 and t2. For example, at t'1, we get the value x of t'1. And at t'2, we get x of t'2. And at t'3, we get x of t'3, etc. all the way up to t'n, where we get x of t'n. Sum all those values up, and divide by the total number of points, n. Now we have a more accurate formula for finding the average position. Note that the more points used between t1 and t2, the more accurate the average position will be. If we have a graph of x versus time, we can use it to calculate the average position of the point between t1 and t2. We can do this systematically by adding x of t1, x of t1 plus delta t, x of t1 plus 2 delta t, x of t1 plus 3 delta t, etc. until x of t1 plus n delta t, where t2 is equal to t1 plus n delta t and delta t is a constant time increment that we choose. Then divide this sum by the number of points plus 1. Note that we need to divide by n plus 1, rather than n, since there are n plus 1 values that we are averaging. Now let's multiply the numerator and denominator of the above equation by delta t, and we get the shown equation. We know that t2 equals t1 plus n times delta t. Therefore, n times delta t is equal to t2 minus t1. Substituting t2 minus t1 for n delta t, we get the next equation, where the denominator is now t2 minus t1 plus delta t. This equation can be rewritten more compactly using the summation symbol, as x bar from t1 to t2 is approximately equal to the summation from I equals 0 to I equals n of x of t1 plus I delta t times delta t divided by t2 minus t1 plus delta t. Note that I is an integer that can take values of 0, 1, 2, 3, etc., up to n. Note that n, or the number of x values that we add from t1 to t2, is equal to t2 minus t1 divided by delta t. Therefore, as delta t becomes smaller, n becomes larger, and subsequently our estimate of the value of the average position gets better. We get the exact value of the average position in the limit when delta t tends to 0. And since delta t tends to 0, we can eliminate delta t from the denominator. And we get the following equation, with the denominator now just t2 minus t1. Then recall that the limit, as delta t tends to 0, of the summation from 0 to n, of x of t1 plus I delta t, times delta t, is the definition of the integral of x of t, dt, from t1 to t2. So now the average position equation can be written in a compact form as x bar from t1 to t2 is equal to the integral of x of t dt from t1 to t2 over t2 minus t1. On the x versus t curve, we can graphically see what the summation looks like for x of t1 plus x of t1 plus delta t, plus x of t1 plus 2 delta t, etc., times delta t. First let's take delta t and distribute it to each term inside the parentheses, and we get the following equation, where x of t1 times delta t is the small rectangular area with a height of x of t1 and a width of delta t. Note that the height is the distance between the point on the horizontal axis, at t equals t1, and x equals 0. And the point on the curve, at t equals t1, and x equals x of t1. And similarly x of t1 plus delta t, times delta t, is the small rectangular area, with the height x of t1 plus delta t, and width delta t, and so on. Summing up all these small areas, gives an approximation of the area under the x versus t curve, which we can denote as A from t1 to t2. As delta t tends to 0, the exact value of the area under the x of t curve from t1 to t2 is equal to the integral from t1 to t2 of x of t dt. So we can rewrite our expression for x bar of t1 to t2, which we obtained in the last slide, as A from t1 to t2, over t2 minus t1. Note that the height of all of the rectangles are measured starting from the horizontal axis, at x equals 0. Note that you can use the slider bar to change the value of n. And see that as n becomes larger, the approximation becomes more accurate. When you'd like to continue with the lecture, please press the play button. Now you can interactively use the sliders shown here to change the values of the starting time, or the ending time, or to change the value of the number of points n. Use the mouse to drag the slider bar, or just type directly into the input box and press the Enter key. Note that as the value of n increases, the approximate formula for the average position gives a value that is closer to the value given by the exact formula. When you'd like to continue with the lecture, please press the play button. Let's take another example of calculating the average position in a time interval. This time with x of t is equal to 3 times the sine of t times 2 pi, over 10. The average position from time t1 to t2, which in this case is 0 to 10, is equal to the integration from 0 to 10, of x of t dt, over t2 minus t1. Then we can break the integration into two intervals. One from 0 to 5, and the other from 5 to 10. The integration from 0 to 5 of x of t is 9.55, and the integration from 5 to 10 is negative 9.55. And so the average position, for the time interval from 0 to 10, is 9.55 minus 9.55, over 10 minus 0, which is equal to 0. So in this example, the average position is 0, even though the instantaneous position is mostly non-zero. Now you can interactively use the sliders shown here to change the values of the starting time, or ending time, or number of points, and see the effect on the value of the average position in the time interval that you choose. When you'd like to continue with the lecture, please press the play button. Now let's derive the relation between the instantaneous position of a point as a function of time, and the average velocity of the point in a time interval. If we know the position of a point at two different times, then we can easily calculate the average velocity of the point between these two times. For example, if Alice is moving along a linear path from home to work, and at 8:10 a.m., Alice is 1 kilometer away from home, and at 8:30 a.m., Alice is 4 kilometers away from home. Then what is Alice's average velocity in the time interval from 8:10 a.m. to 8:30 a.m.? Recall that velocity is distance per unit time. In order to calculate the average velocity, we divide the difference between the positions at time t2 and time t1, or 4 minus 1, by the difference between the two times, 8:30 and 8:10. This gives 3 kilometers divided by 20 minutes, or 0.15 kilometers per minute. So in other words, in order to calculate the average velocity of a point in the time interval t1 to t2, we need to know the position of the point at time t1, or x of t1, and the position at time t2, or x of t2. Then we divide the difference of positions, or x of t2 minus x of t1, by the difference in the two times, t2 minus t1. In the last section, we derived the equation for the average velocity. In this section we are going to rewrite this equation, in another way that's often useful. We start by defining t2 as t1 plus delta t, and then substituting t2 into our velocity equation. We get that the average velocity is equal to x, at time t1 plus delta t, minus x at time t1, divided by t1 plus delta t, minus t1, or delta x, over delta t. So now we have just derived another equation for average velocity, in terms of the total duration of the trip, delta t, and the total distance traveled, delta x. In the case of the example that you just saw, delta t is equal to 8:30 minus 8:10, which is equal to the duration of the trip, 20 minutes. And delta x is equal to 4 minus 1, which is equal to the total distance traveled of 3 kilometers. We just derived two equations for the average velocity of a point in a time interval, in terms of the difference between the position of the point at the end time, and its position at the start time, which is the total distance traveled, and the end time minus the start time, which is the length of the time interval or the duration of the trip. Suppose we have a graph of x versus time, x of t, which defines the value of x at any point in time. We can use this graph to calculate the average velocity of the point between any two times that we choose. These equations are valid for any two values of t1 and t2. For example, we can change the location of t2 and calculate the average velocity between t1 and t2. Note how x of t2 changes when t2 changes, and accordingly, delta x changes, and also the average velocity value will change accordingly. Or we can change the location of t1, and again, calculate the average velocity between these values of t1 and t2. Note that to calculate the average velocity of a point in a time interval, we only need to know the value of the position of the point at the starting time and at the end time. We don't need to know what the point is doing in between t1 and t2. The point can be moving way below x1 or way above x2. In other words, the shape of the x versus t curve between times t1 and t2 can be anything, and the average velocity will not change. All that we care about is the total distance traveled by the point from the starting time t1 to the end time t2, which is x of t2 minus x of t1. Now you can interactively use the sliders shown here to change the values of t1 and t2, and see the effect on the average velocity. Use the mouse to drag the slider bars, or use the right and left arrow keys on the keyboard, when the slider is activated, to move the slider bar a little to the right or left. To activate a slider, just click on it, and a red border will appear around it, to indicate that it is active. When you'd like to continue with the lecture, please press the play button. In the last slide, we derived the formula for the average velocity in a time interval, given the instantaneous position at the beginning and end of the time interval. We can rearrange this equation to get the position at either the end of the time interval or the beginning of the time interval, given the average velocity and the position at the opposite end of the time interval. So we have x of t2 is equal to t2 minus t1, times v bar from t1 to t2 plus x of t1 and x of t1 is equal to t1 minus t2 times v bar from t1 to t2 plus x of t2